Very good morning to we hope we hope everyone had an enriching and insightful experience during the morning session of the seminar. As we begin the last seminar session of this day, we are equally excited to continue our journey of exploring emerging technologies and innovative ideas in the field of energy and future electronics. I kindly request Dr. S. Sivasakthi sir, Professor and Head, Department of EEE, to present the token of appreciation to our esteemed resource person, Professor Dr. R. Govindaraj, Assistant Professor of Physics at Sri Sivaramakrishnan Nadar College of Engineering, Chennai, with memento and bouquet. Thank you, sir. Now I invite.
It is a great honor and privilege for us to welcome our distinguished chief guest, Dr. R. Govindaraj sir. He is an assistant professor of physics at SSN College of Engineering, Chennai, and he is a Baba Atomic Research Center certified radiation safety officer and serves as a institution's I-stream coordinator also. And he is the faculty in charge of several. He joined the Department of Physics at SSN Institution, Chennai. And he successfully completed BRNS sponsored project with worth of rupees 50 lakhs. And his research focuses on nanomaterials, crystal growth, energy materials, third generation solar cells, including perovskite and dye-sensitized solar cells and energy storage devices. He made a significant contribution to the field with approximately 80 peer-reviewed journals, publications, and 2 book chapters. And he is a lifetime member of Material Research Society of India and Indian Association of Crystal Growth. With immense respect and pleasure, let us warmly welcome Dr. R. Govindaraj sir and express our gratitude for being with us.
Respected Principal, Head of the Department of EEE, Periyar sir, thank you for your kind invitation, sir. Good afternoon. Today I am going to talk about two generation of solar cells, third generation of solar cell. There are three generations of solar cells. We have crystalline silicon based solar cells, that is first generation. We have thin film solar cells. Each generation of solar cell have certain advantages and limitations. Okay, in first generation solar cell, almost 90+% is occupied by first generation solar cell, that is single crystal silicon. Crystalline silicon have two things, multi and mono. Mono means single crystal silicon. Okay, using single crystal of silicon one can make solar cell. Okay, there are different. Okay, thin film is very small percentage, less than 5%. Most of them are cadmium telluride. So why we need thin film based solar cell? Any idea? Do we need solar cell first? Do we need energy? Why we require energy? Any idea? What is the cost of electricity here? So how many of them using mobile phone? Almost everybody. You know how many units we are spending every month? Units of electricity at home? Approximately, can you tell me how many units we are spending, consuming? What is the power requirement of one small bulb or fan? Somebody trying to answer. What is the answer? Huh? Good. 41. So I'm not going to ask other questions. Okay. Okay. In second generation solar cell, mostly people use cadmium telluride amorphous silicon based solar cell because in second generation solar cell we require only less material, almost 1000 times lesser than the crystalline silicon. To make crystalline silicon solar cell, we need to give at least 200 to 300 micron thickness of single crystal silicon. Of course, there are processes to make solar cell. So the wafer thickness, the silicon thickness is close to 250 micron. On our average, I am telling today people are looking 150 micron also. So to generate 24% of power conversion efficiency, we need to spend 250 micron thickness of silicon wafer. Whereas in the case of cadmium telluride or amorphous silicon, they are thin film, vacuum based deposition process. Okay, we are spending only few hundred nanometers, less than 500 nanometers, sometimes even less. You see how much we are reducing the material. You know how we are producing silicon? Sand. From sand we are producing silicon. So it must be SiO2 form. We have to extract silicon from SiO2. So many processes are involved. I am not going to talk about the extraction process today. I mostly today I am going to talk about the third generation solar cell. In second generation we have less material, but most of them are toxic. Cadmium telluride, they are toxic materials. Okay, so in third generation solar cell we have again less material but very affordable. So you can make solar cell in your laboratory itself. It's very simple process. Unfortunately, it has some stability issues and efficiency limitation. The world record efficiency of single crystal silicon today is 26.6%. So what is the percentage, sir? We are giving 100%, 100 milliwatt per centimeter square as an input, light irradiance I am talking about. 100, out of 100 we are getting only 26%. Got it? So we could able to convert only 26% in silicon. Whereas in the case of cadmium telluride we are getting close to 19%. So out of 100% of illumination we are getting only 19%. Okay. Third generation solar cells is a very interesting area. Recent days people are looking at. There are three technologies there in third generation: organic solar cells, dye-sensitized solar cells, perovskite solar cells. The third one, the perovskite solar cell, is very recently emerged. It's very interesting area where a lot of people are working. The efficiency within short span of time, less than 15 years, the efficiency reached close to 27%, of course, just above the silicon. But the problem is the stability. Stability is not good as the silicon. Silicon is well matured technology. That's why I told in the beginning, more than 90% is occupied by the crystalline silicon. They are very rigid, solid. So you can use for more than 24 years. But other solar cells are not like that. Perovskite, I told you, the efficiency is just above the silicon. But the stability is very big issue. So people are trying to investigate to arrest those stability issues with different methodologies. I am going to talk about one of them, how we fabricate solar cell with improved stability. Okay? If you have any questions, please ask me. In between also I will try to answer. He is the main person in our institution. He is Professor P. Ramaswamy, is legend in the field of crystal growth. He is my supervisor also. So he produced 1,000+ publications, journal papers. On his name, I have one patent also. Sankaranarayan Ramaswamy. Sankaranarayan, he introduced one method to the scientific society. What happened? You are so excited.
Students, please silence.
Okay, keep quiet. We'll continue. Otherwise, I will not leave you. That I made one small solar cell. They are non-toxic in nature, but the efficiency is less. So there are multiple of opportunities in India, not only in India, in abroad also, particularly in solar cells, third generation solar cells. In third generation solar cell, stability is one of the big issue, particularly perovskite. And also it has lead content, lead, toxic. Okay, to overcome the limitation of these things, the toxicity of lead and stability, people are trying to investigate alternative materials. In that aspect, I made silver bismuth iodide. It's very affordable and less toxic also. I made 4% efficiency. How much? 4%. Silicon is what is the efficiency? So I have to travel a long way from 4 to 26. But it's not so easy. When I started my research career, started with 0% efficiency. My students struggled so lot. Then we investigated so many materials to reach 21% efficiency in perovskite. 21, but the second person who is Chen, Dr. Chen from Taiwan. He is the one who helped me in getting high efficiency solar cell. I will tell you later on. So I would like to acknowledge that. They are the pillars, my research scholars. They are the one who make all sort of solar cells. I will not come there because it's not okay. So I will introduce first the solar cell. Then class different types of solar cells. Dye sensitized solar cells, so affordable one, perovskite solar cell, and we face some stability issue, and we also made some progress to restrict the stability issues and summarize. I will summarize the results. So the process of generating power in around the world. So we have renewable and non-renewable sources. Today I am going to talk about renewable source, particularly the solar. Okay. So this is the energy map. You see energy resource map. Our country has significant amount of energy we are receiving. Most of the states you see, we have good amount of energy, sun energy. We have sun energy. Okay, so we have to harvest those energy with the help of what? Solar cells. Okay, so presently we are using silicon. It is occupied more than 90%. Nanometer, see where the wavelength. So only 5% of energy in UV region. We have 43% of energy in visible. 400 to 700. Then afterwards we have near IR region, 52%. Okay, no single material available to harvest the entire energy. This is the energy we received on our surface, Earth's surface. No single material is available to harvest the entire energy. Okay, each material having certain limitations. Okay, and advantages of course. For example, silicon. Silicon can work from 400 to 1100 nanometer. It can harvest only from 400 to 1100 nanometer. After that, silicon solar cell will not work. Again, the UV region, though its percentage is very less, it will not work. So we have to identify right material to capture the energy. That's why people looking for integration of 2 different or 3 different solar cells. It will work in different wavelength region. For example, silicon, it will work till 1100. Afterwards, some other material. So we can cover the entire spectrum. Entire spectrum is still, even after making 2 junction, 3 junction, also people will not cover the entire region, but we can improve the efficiency. Means multi-junction, tandem. In this way, we can increase the efficiency. Okay, but most of the photovoltaic material you see, they mainly concentrate on visible. Why? You have answer here itself. Because visible in shorter spectrum, you have more energy. You see, that is why we are concentrating on visibly active materials. Most of the photovoltaic materials are visibly active materials. There are 3 types of materials: insulators, conductors, semiconductors. What is the band gap of semiconductor like silicon? Very good, ma. Let's give a round of applause. What is the band gap of germanium? Very good. Okay. Those 2 materials are very good materials for photovoltaic application because it will absorb more amount of energy from the incoming photons. Got it? Then gallium arsenide, I don't want to ask more questions. We'll stick to silicon only. Okay. So likewise, as I said, there are 3 types of materials: insulators, semiconductors, and conductors. Okay. For solar cell applications, mostly people use semiconductors. The band gap should be close to 1.4 to 1.5. Then only we can get more maximum number of power conversion efficiency. Okay. What is meant by solar cell? Of course, I given that detail here itself. What is meant by solar cell? Solar cell is a device which converts electricity directly from the sun. Got it? Okay. So this is a simple silicon-based solar cell. So the moment we shine the light over the device, the electron-hole pair separation process will occur. The charge carriers are collected at the electrode interfaces. Okay, so after the usage, the charge gets again come back to the solar cell. This is how the solar cell works. Okay, so you should have good material having good absorption coefficient. So what is mean by absorption coefficient? So each material, as I said, will not work entire spectrum, right? So every material have different absorption coefficient. For example, silicon will work in the particular region. Their absorption coefficient high. For example, in the previous spectrum, here certain material have higher absorption coefficient. Means how much of amount where the material is absorbed in a particular with a particular thick essential to get better performance efficiency. This is a simple diode. Okay, here you have current, here you have voltage. You see here, just we perform JV characteristics. You see, in fourth quadrant there is no pattern. Means under dark condition it will not give any pattern. The moment you shine light, okay, so diode is nothing but your solar cell. The moment you shine light on your device, you see there is a shift. There is a increase in current. Got it? Intensity, light, you see more of photons of your device. Now, a solar, beautiful IV curve. Here you see the area is more. The area is more means you are harvesting more power. It is a simple concept. Okay? This is a typical pattern of JV characteristics. You see that there is a square pattern. This is called fill factor. In the entire spectrum, you see in the y-axis you have current, the x-axis you have voltage. The combination of current and voltage gives you, if you multiply the current and voltage, what will come? You are triple students, ma? Power. So to operate any electronic equipment, we require power. It's the combination of voltage and current. So your solar cells will produce more power. There is a point called P max.
Maximum power point.
Very good. Maximum power point. So here you have maximum power. Here voltage is fine. What about current? Zero. We can't use it, right? If you go there, can you use here? What happened? Zero? We have zero power. Okay, fine, yeah. Zero power because we don't have voltage here. Correct, you are correct. Okay, so using this thing, you can extract the power point. Okay, this is the fill factor equation. This is the efficiency equation. I am not going to talk about much on this because you are familiar with these equations. This I told already in the beginning. Different types of solar panels. So there are 3 generations of solar cells. So the first 2 are first generation solar cell. Efficiency is very high, but it has some limitations. We have to put excess of energy or material to get more efficiency. But in the case of thin, it's lightweight, but it has some toxic things. To make silicon wafer, you see chunk from sand to silicon. So we have to buy a chunk made up of SiO2, then we have to process it, we have to melt it to get crystalline silicon. This is a process called Czochralski process. Czochralski means he is a scientist who invented the technology to grow single crystal silicon. You see, this is the silicon. From the silicon, we have to make wafers. We have to chop it. Okay, this is the kind of wafer. After that, we have to make cells. There are different methodologies to make cells. I'm not going to talk about now. More. So they started with some technology. For example, DSSC in 1991, they started with 6% efficiency. In 2014, they arrived with 13% efficiency. Silicon, very long, but 1950s they started. Now the efficiency is 26%. Like this, all the information you can see for all sort of materials, starting from first generation, second generation, and third generation. More details you can see from this website. This is the efficiency record of crystalline silicon solar cell. Very recently, 2026, on Chinese groups, industry, 26% of efficiency they reported for silicon. So, 3 generations of solar cell. First generation made up of crystalline silicon. Second generation, cadmium telluric amorphous silicon, CAGS. In third generation, of course, there are different varieties. And today I'm going to talk about these 2 things, dye-sensitive solar cell and perovskite solar cell. In our laboratory, we are doing multi-amorphous dye-sensitive solar cells and perovskite solar cells. Okay. Now we will come to the dye-sensitive solar cell, the first topic. Is Ringel, is Michael Gratzel. Both of them from Switzerland. They are the one first to introduce dye-sensitive solar cell. Silent one. Okay, fine. You see here, we have FTO. FTO means fluorine doped tin oxide. It's a glass and conducting substrate. On the other side also we have FTO, fluorine doped tin oxide. It will allow light and also will conduct electricity. Okay? You see here, there is a green ball. So many balls are here. They are TiO2, titanium dioxide nanoparticles. Okay, so we use 10 micron thick particles by printing process. Okay, on top of FTO, this is the commercial substrate, glass substrate, conducting substrate. It will allow the light and also will conduct electricity. Okay, so on top of it, we deposit 10 micron thick of TiO2. Silicon, how much we use? 200 to 250 micron. Okay, we use only 10 micron thick of TiO2. Okay, you see there is a small red color balls. What they are? They are dye molecules. Okay, in silicon based solar cell, silicon is the active material. Here dye is the active material. Visibly so active. Okay, and we have mediator called electrolyte. I will explain in detail. Then we have a platinum electrode. So this is called counter electrode. In one side of the FTO substrate, we deposited thick layer of TiO2. On top of it, we have dye molecules. On the other side, we have FTO. On top of it, we deposited platinum. So this is called counter electrode. This is called working electrode. Okay. In between, there is a mediator, electrolyte. Okay. The moment you shine the light over the device, what will happen? The dye molecule get excited. Okay, the excited molecule will inject the electron. Okay, at the interface of TiO2. The TiO2 carries those charge carriers efficiently. Okay, and after utilization, it will go to the counter electrode here. Okay, then there is a hole. Okay, the moment you shine the light with photon, there will be generation of charge carriers, right? Holes and electrons will be there. The holes has to be transported to this point. So for that, one mediator view 100 nanometers. That's it. Very simple process. Okay. So instead of TaO2, people can use zinc oxide, tin oxide also. But TaO2 is the best material because it gives lot surface area. We require good amount of surface area so that we can accommodate more number of dye molecules. Okay. I'm not going to talk about the energy level diagram and all. You people will get tired. So dye-sensitive solar cell. So maximum efficiency people have reported 13% efficiency to 5 years ago. So after that there is no progress. Means the efficiency went till 13%. After that people try to improve the efficiency, but the efficiency limit will stop there itself. Okay. Why DSSC compared to first generation and second generation solar cells? We have certain advantages. It's low cost, okay? So we can make tons and tons of TaO2 by pyrolysis process and solvent process. They are non-toxic, okay? We can fabricate solar cell in our laboratory itself. We no need to go for complex vacuum-based process or high temperature process like silicon and amorphous silicon, cadmium telluride and all. In your lab itself, in your chemistry physics lab itself, you can make such solar cells. Okay, they are lightweight. You can make solar cell on flexible film like Kapton kind of film. You can make solar cell, flexible solar cells. And you can make different colors of solar cell because each dye molecule have different colors, right? So based on that, you have different colors of solar cells. Of course, it has some challenges as well. The stability issue, as I said, the efficiency is limited. So you see there is a diagram here, video also here. You see we are shining the light on DSSC. So you see the dye molecules get excited. The excited molecules inject electrons to the TaO2. Okay, the holes are moving towards the counter electrode through the media called electrolyte. So where we can regenerate the holes. Okay, this is how the dye-sensitive solar cell works. So there are issues. So the leakage of electrolyte, we are using liquid-based electrolyte. Okay, so let's get us to the photoanodopy. But sometimes what will happen? You see the dotted lines. So they are recombination process. You see. So sometimes in the lab, the injected electrons will interact with oxidized piece of diamond, oxidized piece of your electrolyte pod. So through the way you can means the recombination process will occur. We need to avoid those recombination process. Then only we can improve things. So this is a particle and one is a kind of dye molecule attached to the surface of the TaO2. This is the spectral response of the particular dye-sensitive solar cell. You see, IPC is a keyboard powered with dye-sensitive solar cell. This particular thing is available in UK, and here also in the backpack you see the dye-sensitive solar cell flexible panel. So you can charge your mobile phone or your laptop using this one. One more advantage is that this kind of solar cell will work in ambient light itself. In this room itself, this kind of solar cell will work, but silicon will not work. You see there are different products based on dye-sensitive building integrated photovoltaics, particularly you see the windows and all, made up of dye-sensitive solar cell. They are in Switzerland. Some of them are in Japan. This is one more demonstration in Japan. So you see different colors of solar cell, means different dye molecules they use, synthetic dyes they are, to produce electricity. So one girl is charging her bike with different dye-sensitive solar cells, flexible solar cells. So Solaronics is the company who produce large amount of components for DSSC. Some panels. These are all the companies involved in commercializing the DSSC technology. So these are all the key components, as I said in the previous slides. Okay, so the nanomaterial, TaO2. TaO2 is widely used semiconducting materials in many places. It is a very good, important material in DSSC. It's out of DSSC. It produces a lot of beautiful features like high surface area for better die loading. The energy gap is also very important. So the conduction band position of TaO2 should be close to your die molecule. I'm not going to talk about much. You will you will not understand much. I will not go very deep into that. Silent. So TaO2 nanoparticles, TaO2 generally have three phases: anatase, bruchite, and rutile. Means three crystallographic phases. So the anatase phase is more important for photovoltaic applications because it produces good amount of surface. And the bandage position also is very important, crucial parameter. It should just below the LUMO level of die molecules. Then only we can capture the charge carriers efficiently, and its mobility also very good. So we have to prefer the anatase phase, this one. There are ways to produce TaO2, salt gel, hydrothermal, co-precipitation. Several methods are available to produce TaO2. In our normal laboratory itself, we can make TaO2 nanoparticles efficiently with good surface area. So in our laboratory, we have most of the process. TaO2 nanoparticles. Generally, people use 10 micron thick, as I said in the beginning. TaO2 nanoparticles. The size of the particle is close to 22-25 nanometer. There is a limitation here. You see a lot of grain boundaries. We should avoid the grain boundaries. If you avoid the grain boundaries, you have to use alternative nanostructure. You see, so electrons are traveling in a different direction. Wherever the nanoparticle touches each other, and there only we are collecting charge carriers. Okay, so in order to overcome this challenge, people have tried with different architecture, nano rods, nano tubes and all. So that gives you the channeling effect. Okay, so electron can easily travel via the rods. So in this way we can efficiently extract the charge. Means you will get better current actually. So that is why people use one-timers nanostructures, nano rods, nano tubes, nano fibers and so on. So in our laboratory we tried both. Okay, and also combination of these two also we tried. You see here in our approach, you have rods and particles mixer. So we are not losing the surface area. And also we have the rods that gives you the channeling effect. Ultimately you can enhance your current density in your device. Okay? And this is because conventions have a lot of conventional nanoparticles, lot of disadvantages. Method if you are interested, you can reach to me. I will explain in detail. I am not going to discuss about this. Very simple based solution process one can construct easily. And then we have to in the rest of TaO2, we have to stand some cells. Okay, we use X-ray diffraction. X-ray diffraction measurement. This is structure. Of course, it has peaks. With known databases, we have to confirm whether it is TaO2 phase, bruchite phase, or rutile phase. Okay. This material contain mixed of phases. Then we performed TM analysis, transmission electron microscope analysis, to see the morphology of the synthesized material. It has particles and rods. Okay. Then crystalline structure also we have to see. For select a direction, see the bright dot. Amorphous may not have such dots. The surface area is very much required to accommodate more number of dye molecules. So, we discussed about making TaO2 rods and particles, mixture of rods and particles with one method called hydrothermal method, solution based method. Now we are going to see how to fabricate solar cells, dye sensitized solar cells. Okay. So this is the powder, TaO2 powder, synthesized powder, just to be grinded, okay, to make slurry of TaO2 with some chemical. First we should place our FTO substrate. As I said in the beginning, FTO substrate we used glass. It is transparent as well as conducting. So we placed our slurry over our FTO substrate. Then we, with the help of blade, we coated. You see here the coated part. Then we heated to 500 degrees because heat treatment is very much residential because we need to have anatase TaO2. To get that phase, we require heating process. Okay. Then we prepare dye solution. Okay. Dye solution. Now we completed first part. The second part is another FTO substrate. We develop platinum. Because the thickness is very less. So then we both photo out and we join together. In between we introduce electrolyte. This is our final device, dye sensitized solar cell device. They have to do IV measurements under standard light conditions. Okay, simply we can't keep here to measure actual measurements. We need to mimic our sunlight. For that, we need to use standard solar simulator. So class AAA condition we have to follow. Okay, we have dedicated class AAA solar simulator in our laboratory. So under solar simulator, we perform JV measurements to see exact efficiency of the fabricated device. So this is the performance of our fabricated device under standard condition. You see, with our rods and particles, improved condensity. As I said in the beginning, there are so many parameters we can extract. You see, there is a huge improvement in the current density. Means our rods are giving better channeling effect because of the straight channeling. It efficiently extracting the charge carriers from the dye molecule. This is one more procedure. I am not going to talk about now. The same kind of thing, only we modified only the synthetic chemistry part of TaO2 making process. This is the same again methodology only. We modified only the TaO2 part. So conventionally we used electrolyte. Through the gap we usually inject the electrolyte. There is always the leakage issues. So in order to avoid that, we made one small hole on the FTO substrate. Through the hole we inject the electrolyte. So in this way we can arrest the leakage. So you see there is a sealed device. So we made one small hole in the FTO substrate. Through the hole we inject the electrolyte. Then we, with the help of one polymer film, will seal the device. So we can improve the stability by sealing process. You see again the improvement in current density here also. And we perform the stability analysis for our fabricated device. From the solar cell, 9% efficiency we obtained with the combination of rods and particles. So we started the game in 2012 with 0% efficiency and 0% of knowledge also. So after over the period of silent part. So from after that, we used different approaches to get 9% efficiency. We took this much time to get this much efficiency. Means lot of effort we have to put to get that much efficiency. So well, best record efficiency is 13. We reached close to 9% in DSSC. So likewise, we prepared several nanostructures with different methodologies like hydrothermal, sol gel, and so on. You see beautiful spheres. They are mesoporous materials. Okay. They are very good for photoanode and dye-sensitive process. You see, this is very special to me. So during my PhD, you see the well-aligned zinc oxide nanorods. I did this work by hydrothermal process. We made small seed layer of zinc oxide by spin coating process. Then I took that particular substrate, I did hydrothermal process, okay, with the zinc nitrate salt. You see a well-aligned zinc oxide rods, okay. This is a very beautiful structure I got, and that's why I am keeping. So I prepared so much of nanostructures. So much of nanostructure with the different methodologies, hydrothermal, sol gel, and different combination of solar structures we used. So you see the progress. We started with the commercial one, 4.4% efficiency. We reached close to 10% efficiency with over a period of time. Likewise, one of my colleagues also did a significant amount of work in dyes. You see the efficiency improvement. Of course, less only, but making dye is not so easy. So electrolyte also we tried. Then counter electrode also, platinum is expensive. To avoid that, we introduced several other structures to get better efficiency. So maximum we got close to 7% efficiency. So another exciting topic, perovskite solar cells. Dye-sensitive solar cells so far we discussed. It has some efficiency limitations and stability issues. Okay, the perovskite is very similar to the dye-sensitive solar cell, but it has the efficiency close to 27, just above the silicon solar cell, 27%. Well record efficiency I am talking about. This is the structure. Okay, so you see here. In dye-sensitive solar cell, you have FTO. You have FTO, both sides. You have TiO2 particles. On top of it, we have dye molecules. Okay, so simply Miyazaki group in Japan, they replace the dye molecules with this structure. Perovskite. So in the place of that red ball, they replaced this structure, dye. Okay, they got efficiency 3.8 for this particular combination. For this one, and this bromine content containing perovskite having 2.6%. But immediately the devices were degraded. Then people thought, instead of electrolyte, can we go for solid hole transfer material? Then the entire structure itself they changed. So instead of regular DSSC, they used going very deep into that. So you have TaO2 again, okay. You have perovskite. Instead of dye, perovskite is there, and you have solid hole transfer material. Okay. Then gold. Gold we have to use to collect holes. Okay. So these are all the materials involved. So currently the best reported efficiency is 27% efficiency with Chinese drew. So these are all certified efficiency. Unfortunately, no single Indian laboratory presented in this chart. So we have to we have to work very hard to come in this. This is the standard chart, National Renewable Energy Laboratory chart. Every year they are published. Whenever people are getting highest efficiency, people are certifying it here. Okay? Of course, here also there are different industries involved. So in India particularly, in Haryana, one industry started doing the things, perovskite solar cells. So they are doing glass-based solar cell, perovskite solar cell and flexible solar cell. It has some challenges like in DSSC, stability issues. Under UV light there is a stability issue. Then the effect of heat, there is an issue. And people use noble metals like gold, silver, okay, as a back contact material. Advantage is that we can make solar cells simply using solution process approach. So I am not going very deep into this. The structure itself having a lot of issues, uncoordinated lead ions, PB lead cluster and so on. So in order to avoid such things, my student did one passivation engineering approach to passivate the defects in the system. So he took one organic molecule, 2-APT, 2-benzamino-thiazole unit. It has sulfur and nitrogen atom. It coordinates with uncoordinated lead ions in the perovskite system. You see, with conventional methyl ammonium leaded, it's perovskite, you have the pinholes. So after introducing the 2-ABT system, you see there is no pinholes. He used 3 different concentrations. You see the pinholes we avoided. That act as a decombination centers. Okay. So we performed U visible analysis to see the band gap. You see there is no change in the peak position, means our structure is so stable. Also we did the contact angle measurements to see the hydrophobicity nature of the, because it efficiently absorbs the water molecule, it deteriorates the cell over the period. So to avoid that, my students are introduced some organic molecule. So you see from the study, the hydrophobicity is increasing with our molecule. So this is the structure we used. So we have FTO nickel oxide, and we have one interfacial layer perovskite, one interfacial layer, and we have one metal contact background. So these are all the steps. I'm not going to discuss about. These are all the perovskite devices we made in our lab. This is a JV performance of our fabricated device. So far we discussed about the disensitive solar cells and perovskite solar cells with different morphology of KO2 and perovskites with passivation strategy. Again, I am thanking my collaborators and guide. So the facilities available in our campus. So we have DA system to grow 800 kg of silicon. So you can come and see if you have any time. Please do come. We can grow silicon of 800 kg. So we have PECVD system to deposit thin film of amorphous silicon. Sputtering system also we have. We have a screen printer to deposit films, spin coater. So I am the facility in charge of big facilities, X-ray diffraction, spectrophotometer, sun simulator, and several other characterization techniques, glow box. Okay, thank you. Thank you for your patience.